Greetings, Earth scientists, and we are here today to learn about the ocean floor, ocean resources, and waves. 71% of the Earth's surface is covered by ocean water. That potentially has the chance to rise if we have a major transgression. You'll be learning about those shortly. And in geologic past, that certainly has happened over at least 6 worldwide sea level rises that covered most of the continents have occurred in geologic past. One way we know that is that there is ample limestone, which is an ocean-derived marine carbonate rock that forms in marine settings that are usually shallow epiric seas. So we have those even in the middle of North America. So it's hard to believe that you have it all the way up to Canada. We have it through Montana, Kansas, Nebraska, the Dakotas. We have it right here in Texas, all over the place. We can see this on the continent. And we're not alone. All the other continents have similar types of stories to tell. So when you think about the mass of continents, that just makes the remaining percent of 100, which is 29%. So continental mass, while it's our most important resource we have for humans to live on, there's quite a bit of resources available in that 71% of the Earth's surface. When you look at the Earth's oceans, there are literally 5 major oceans. The Arctic is at the North Pole. What we now call the Southern Ocean down here, which used to be called the Antarctic Ocean but has been renamed to the Southern Ocean. Then there's the Pacific, the Atlantic, and the Indian. Each one has its own characteristic. So when you take a look at the world's oceans and compare it to the amount of water we have, let's talk about what we have in terms of surface water in the world. About 97.2% of all the water in the world is made up of salt water. So when you look at the remaining 2 to 3%, you're really looking at freshwater resources that come from 2 places, primarily from, well, 3 places. Primarily from ice, then groundwater number 2, and 3 rivers, lakes, streams, and surface water. So when you take a look at that amazing amount of water, let's look at the size of our oceans and compare the size of each one and their importance. Obviously, the Pacific is the largest. That would be a good test question. The Atlantic comes in number 2, Indian number 3, the Arctic number 4, and if you count the Southern Ocean, it's 5. It's the smallest one. So when you look at the average depth and elevation of ocean topography versus land, the ocean's average depth is 12,234 feet. Well, the average elevation of land is 2,756 feet. So there's a considerable difference in terms of looking at how the ocean is set up. The deepest ocean feature we have currently is the Marianas Trench, which sits at 36,161 feet. That's absolutely insane. So you'd be looking at this particular structure right here. When you think about the highest mountain in the world, it's 29,029 feet. That's Mount Everest. Compare that to the deepest trench, and you could put Mount Everest and sit it right inside of that trench. So these are really important features to look at, because when you start to zoom in, I want you to realize that our interesting depth here, when you start looking at the oceans, these 3 oceans aren't that different. This is the deepest one. The Arctic is much more shallow. There's a reason for that. But we have a feature, and matter of fact, all 3 of these oceans that have deep sections called deep sea trenches caused at subduction zones that you learned about in the geology section. So the Pacific is the largest and has the greatest depth. It isn't as significant a depth change as you'll see comparative to the 3 main oceans versus the Arctic. So the Atlantic, being half the size, is not quite as deep, and the Indian Ocean is slightly smaller than the Atlantic, but it's very important ocean basin. It drives some important ocean currents. Arctic Ocean is about 7% the size of the Pacific, so it's a runt. And that is an important ocean basin because it's kind of landlocked in now. And that happened literally within the last 5 or so million years, which actually contributed to the formation of permanent ice packs in that part of the world. Now, ocean sediments come from us from a variety of places. First of all, they come from runoff of land. And as they do, they're going to wash off and they're going to wash into waterways this way. Let's call this an ocean right here. So you might wonder, how do I form sand? How do I form silt? How do I form clay? How do I form carbonate mud? Those are excellent questions. Your sands and silts are primarily created by what we call terrigenous. I want you to say that word with me, terrigenous. Again, terrigenous. Terrigenous means land-derived. And so that's going to be the stuff that's eroding off of continents, weathering and eroding and washing down in water runoff that feeds into the ocean. And so it's going to settle out by size. So the bigger the size, the more or the faster it's going to fall out. Like you see, the sand's going to be a bigger grain size than silt, and silt's smaller than, or silt is bigger than clay. Clay is smaller than silt. So you're like, what about this stuff over here called carbonate mud? What forms that? You could have a little bit of terrigenous material. Primarily, this is made from the decomposition of dead microscopic animals. So it forms lots of things like limestone. That's predominantly what carbonate mud is. So when you're looking at a rock unit, you can determine kind of how it was made and how close to a shoreline it was simply by looking at the sediment size and the character of those sediments. So sand and silt facies form at the beach line or the nearshore environment. The clays or shales form in usually lagoonal settings, and then the limestone facies form in far away from the coastline where you're not going to have much influence from terrigenous material. So there are two important concepts to talk about with oceans when we're looking at ocean levels, especially on continents and with relationships to humans and prior animals that have lived on Earth. There are things called transgressions and regressions. Regressions is a lowering of sea level. And when this lowering occurs, part of the sea that was covered previously by water is now exposed. And so when this happens, you're going to get a shoreline rock called sandstone forming very, very thick, where you're going to see a lot less of limestone forming simply because the environment where the water has shifted is no longer at the right depth to form this. So I'm going to give you an example. I'd like you to think about, let's say, a shot putter in track and field. And then I want you to think about the hurdle jumper. And then I want you to think about the long distance runner. Don't they all have a different kind of body plan? Well, it's because they train differently, and their bodies are made a little bit differently because they train their muscles that way. Well, much like that with rocks, because these rocks that are being formed in transgressions and regressions are a direct relationship to the energy of the water and the character of how far away from the shoreline these rocks are formed. So you're going to have the real bulky sediments like your shot putter close to the shoreline. That would be the sand. And your fine grain muds, which would be this stuff down here, is going to be like your long distance marathon runner. Moving on to transgressions, these are when parts of the land that are currently exposed get covered up by water and a rise in sea level. So the prefix trans means to invade, and the prefix regression means to retreat, or the re means to retreat or pull back. So now if I see a rise in sea level, I'm going to start to form rocks on the land that used to be just regular exposed land that are now forming things like shoreline rocks like sandstone, or if it's a lagoon, it would be making shale. Or if I'm covered far away from a terrigenous input of sediment, right in Waco, Texas, for example, I could form lots of limestone, which is truly the case of what we have happen right here in Waco. All right, transgressions versus regressions. What causes each to occur? So a rise in sea level, aka a transgression, test question, that is caused by the melting of ice caps. You're like, duh. That happens. So as we have a climate warming, which we are experiencing at the moment, this can cause the shoreline to rise where people live. And since a bulk of our population around the world lives within 100 miles of a shoreline, this becomes important. When you have high mid-oceanic ridge activity, remember learning about MORs back in the plate tectonic section? When you have big plate tectonic mountains growing at the bottom of the ocean floor in the form of volcanoes, it's going to push that water and displace it onto the continent. So I'll use an example. You fill the bathtub up too full of water. You get in and you cause a slosh out of the bathtub because you displaced that water. Imagine, instead of it being you, that those are volcanoes at the bottom of the ocean floor. So the more activity you have of volcanoes, the more displacement of water you have at the bottom of the ocean floor. A second thing that can happen is the land can subside along coastlines that could allow it to be flooded. Let's give an example of New Orleans. New Orleans is below sea level anyway, but let's say because they're pumping out so much groundwater, they could actually create subsidence, and that would flood inland more rapidly. Regressions, which is a lowering of sea level, could be caused by something like this, where you start to get massive glaciation or ice ages that form on the globe. When you get a decrease of those big volcanoes at the bottom of the ocean floor is more flat. Subsequently, the water level drops, and so it appears to be dropping in sea level. If you have uplift of the land, meaning like mountains along the edges of continents, that can also lower sea level just because the land is higher and the water can't invade as far or fast. Ultimately, what happens is that we end up with multiple transgressive and regressive sequences in the rock record. So let me kind of point out, this would be a small transgression, a small regression, a large transgression, a medium regression, a large transgression, small regression, big transgression, small regression, little bitty transgression, big regression. Are you seeing these jags here? Well, what's happening is the rocks are going, the rocks are going in and out, in and out. And what's happening is that represents the shoreline moving in, the shoreline moving back out. So subsequently, where I can form sandstone, shale, clay, which is, or should I say, where I can form sandstone, siltstone, shale, and limestone, shifts laterally one way or the other based on if shoreline has moved onto the continent or back out to the ocean. Here are some examples of transgressive regressive rocks in Waco, Texas. The big blocky layers are actually limestone. They weather at a slower rate than the rock layer in between them. That's called differential weathering. And these are clay layers or shale layers. So what you're seeing is, if you come to, this is Lover's Leap in Waco, by the way. If you walk all the way up and start counting all of these layers at different faces of Lover's Leap, there's over 30 of them. So that means we had 30 sea level changes where we had limestone, shale, limestone, shale, limestone, shale. Let me translate. Far away from a terrigenous input, lagoon, far away from a terrigenous input, lagoon, far away from a terrigenous input, lagoon, and so forth. So it was just slight sea level changes to change the environment and the type of rock that could be formed there. So the oceans provide us evidence of this, and even on land. So I can tell you by looking at these rocks that we used to have an ocean right in Waco, Texas. So let's talk a little bit about ocean margins and how they play a role in the study of oceanography and geology for that matter. If you have a passive continental margin, that means that you do not have any plate collisions going back to plate tectonics happening on the edge of a continent. In North America, the best place I can give you that is occurring would be the eastern margin of the continent, so along the eastern seaboard. So what we will see right now in North America, the Atlantic Ocean area is passive. In geologic past, that has certainly not been the case. It has been an active margin, especially during the Paleozoic era. Now, we're going to look at these different pieces of the floor of the ocean and kind of describe what happens in each. And each one has a value intrinsically for money, that we use out of the ocean floor. Let's start with the continental shelf. That's this area right here. So really that's the extension of the continent that just happens to have water on top of it. So if I had a transgression, the continental shelf would actually move more onto land. Okay, so the continental shelf is a very important area because here's why. It's very gently sloping, it's not very deep, and this is what contains a bulk of our oil and gas deposits. You'll learn a little bit more why later, but in a nutshell, it's shallow enough that photosynthesis can occur, so you'll get a bunch of small little microorganisms, things like foraminifera and diatoms. These are things that literally make hundreds or thousands by the square centimeter, and when they die in mass quantities, especially at mass extinction events, they accumulate on the ocean floor, and at this depth it's not too deep to crush them. So they accumulate into layers, and most of them have a small little tiny amount of oil inside of them when that was used for eating and living when they were alive. So when they die, that little bitty amount of oil and material is oozed out and makes hydrocarbon layers. Isn't that neat? So next time you go fill your car up, I want you to have a foraminifera respect moment and go, thank you, because it's those items that give us our oil and gas. Rather remarkable thing. If you see a continental shelf on the same of these areas, you will see a number of different types of deposits. Literally, you'll get more thick deposits right along the coastline right in here. You'll have less what we call terrigenous material out here. But if I've got some kind of a mountain zone that was uplifted, that's going to erode sediments and put that sediment right here. So if you don't have mountains along a shoreline, then you're not going to have as thick a blanket of deposits there. If you have a mountain there, it produces the sediments that are eroding into the ocean. So another part of the continental margin is the continental shelf. Another feature beyond the continental shelf is the continental slope. This is actually a really important area because the detrital or terrigenous material, if you remember detrital from early on in the semester with geology, that's a sedimentary term for rock fragments broken up from other rocks. So if you get this area right here, which is to be the coastline, and it's producing on the continental shelf all those terrigenous or detrital materials, sometimes turbidity currents, which are like underwater tornadoes, will carry that and come down these steep structures right here, which is the continental slope. Do you see these little lines right here? Those are deep submarine canyons. And those deep submarine canyons are caused by these turbidity currents, which we're fixing to look at. So submarine canyons are these things right here. They are the deep gouges, steep-sided valleys that cut into the continental slope. And some seaward extensions of river valleys, they appear where these water bodies have come off of the continent and produced some pretty impressive currents that have scoured out these land masses. You can see one of those right here. But turbidity currents are real, and they play an important role in moving sediments throughout the ocean. This is what a turbidity current looks like, just a sketch of one right here. And it's a dense sediment-laden movement of water. These deposits are called turbidites, and I have actually seen a turbidity current underwater when I was scuba diving. It's not an experience I choose to have happen again. I was in Bahamas, and we were studying off of the Lee Stocking Island, which is where a bunch of stromatolites are, and our team got hit by a turbidity current, so we were holding on to stromatolites for dear life. And I remember thinking, wow, it just looked like a tornado of water. And some of us got relocated from our boat several miles within just a couple of seconds, you know, like a minute or two. We were gone. And they rounded us all up. We all ended up being safe. But I saw the power of a turbidity current and never underestimated what it could do in the ocean after that. So when you're looking at turbidity currents, they can move some of that terrigenous material you see right here and move it down and deposit them at the bottom of these continental slopes, which is where the deep submarine canyons are. So essentially they make big gigantic alluvial fans is what they do. and you can actually see what's called graded beds. We talked a little bit about that earlier in the semester, but a graded bed simply represents where the biggest sediments drop out first because of energy of water, then the next smaller size, so and forth till you get to the tiniest size. And you can see that here's big, next size, medium, small. And so it divides that out because as the turbidity current comes down these canyons, the biggest energy is going to be right here. And as you get further down the fan, you should see finer grained sediments. Turbidity currents can travel at over 100 miles an hour. So these are extremely important for moving bigger material that shouldn't normally move at the bottom of the ocean where there's not that much energy. Another area to consider is something called the Continental Rise. That's this section right in here where the Continental Slope and Submarine Canyons stop, and you get a buildup of sediment on top of it right in here. That's the Continental Rise because that's where the deposition of the turbidity current deposits get put. That can be important because some of those deposits have intrinsic value. When we get to the bottom of the continental edge, which is the Continental Rise, that's where the ocean floor actually starts. You go, but I thought the whole thing was an ocean floor. It really boils down to chemistry of the rock that makes up either type. When you're talking about Continental Slope, Continental Shelf, Continental Rise, we are looking at a chemistry of rock that's different from the basic chemistry that makes up the ocean floor. So the abyssal plains are the primarily pretty flat areas. There are some accumulations that make mounds and hills at the bottom of the ocean floor that's on the abyssal plain, but this is the area that has the thickest accumulation of sediments on the ocean floor. Most of them are from fine-grained settling of dead animals and some terrigenous material from land, and we find these in every ocean basin. So this is a look of just how desolate the abyssal plain is. So let's kind of have a review of the features. You've got your submerged continental shelf here, really important for oil and gas. Then you've got your continental slope, which is this feature right in here with the submarine canyons, and turbidity currents cut that out. Then those sediments are deposited right in here, which makes up the Continental Rise. The Continental Rise eventually fades into the abyssal plain, which the abyssal plain is actually the layers of raw sediment that sits on top of oceanic rock, which is actually basalt. All right, so let's talk about active continental margins. How are they different from passive? If you got an active margin, that means you got some kind of plate boundary working, whether it's a subduction zone, a continent-to-continent plate collision, you've got a transform plate boundary, kind of like San Andreas fault, but nevertheless, these are areas primarily that get squashed and smashed by subduction zones in most cases. So what will happen is you, instead of having a nice continental shelf that's slowly dipping like this, it tends to be fairly abrupt. And you can see that because here's your continental edge and here's this incoming ocean plate, and see how it squashes up all of the continental stuff right here, a continental rock. So you don't have that nice continental slope like you do in a passive margin. Instead, you get deep sea trenches. So this is where we can actually glue on or accrete part of our ocean crust and squash up what used to be layers of sedimentary rock at the bottom of the ocean floor and stick it onto the continent. That's called an accretionary wedge. That will be a test question. So the accretionary wedge is simply where land has been permanently connected to a continent in some kind of plate collision. Very, very common on the western side of our continent of North America, where we have Juan de Fuca in the Pacific Northwest subducting under parts of Oregon, Washington State, and even parts of Northern California. These areas have little or no accumulation of oceanic sedimentary layers because it's an active subduction zone, so there hasn't been time to develop large concentrations of thick sediments. We'll get to that in just a minute. So the deep ocean trenches, these will only be found at subduction zones. These are long, deep, narrow features caused where an ocean plate makes a dive under a continental plate. Most of them in the world are found in the Pacific Ocean basin. Having said that, you can find them in the Atlantic Ocean basin and in the Indian Ocean basin, depending on where you are. So these are sites where oceanic lithospheres are plunging beneath continents into the mantle, and they are usually associated with the melting of oceanic and partial melting of continental crust, which creates active volcanoes along that stretch of land. So that brings me to a couple of thoughts that you need to know about features that are common on the ocean floor. There's two features I want you to learn about, seamounts and guyotes. Let's start with seamounts because they're the younger version of these guys over here. These are volcanics or volcanoes that form at the bottom of the ocean is what they are. And they grow one layer at a time pretty quick. In the case of Hawaii, the seamounts like Loihi, which is the most modern one that's growing right next to the island of Hawaii, that's grown up in about 400 to 500,000 years. And if you take a look at the biggest volcano on Hawaii, Mauna Loa, that grew up in about 800,000 years and became an island. And this blue line right here would represent the water level, let's say the Pacific Ocean water level. So they're growing in less than 1 million years and reaching the surface here. That's pretty rapid volcanism. So what will happen is, since they grow so fast, they're pretty unstable structurally, and they kind of fall apart at the seams once they become above the water level here. So they'll stay that way for several tens of millions of years, sometimes 50 million years, and then they'll come below water again. And they'll either stay looking like this, where they just don't get eroded very well, or they get eroded and break off and make what's called a guyot. So a guyot is the flat top one, and that's a much older feature than a seamount. So seamounts, volcanic seamounts, are, as they're growing up, and as they are called just a seamount, that usually means that they've gone back underwater. If you get a guyot, that's a seamount that's had their top block knocked off, and they're much older features. Why is that important? When we did the deep sea drilling program, when we had World War II and we're mapping out the ocean floor, we got a stunning surprise that the ocean floor was full of these things. And we're like, wow, where do they come from? How did they get there? So we can get a seamount that will emerge as an island, not a guyot, because they used to be a seamount. But eventually they sink because these volcanoes just weigh an incredible amount. To give you perspective, Mauna Loa is 56,000 feet tall. Now, I think we mentioned earlier that Mount Everest was 29,029 feet tall. I want you to do the math on that and realize that it's almost double the size. It's just pretty incredible, isn't it? So these are just monstrosities of the largest features on Earth. So their total relief at the bottom of the ocean floor to their summit is astronomically bigger than something like the total elevation of Mount Everest. Midoceanic ridges are also found on the ocean floor. We briefly talked about these in plate tectonics, but this is important because they are where a hot spot's cooking the bottom of the ocean floor and separating it. And this is where the basalt I mentioned earlier will flood out of these ridges right here and coat either side of the ridge. Well, or even during World War II, we discovered this by doing magnetic flyovers, where we took an instrument to measure the magnetism of rocks. We were actually looking for enemy submarines, and we discovered that the ocean floor was just covered with iron. And that's because basalt's very, very rich in iron. So that's important because there's a mirror image of the lava on either side of the crack, and that can give us an age date for those rocks as well. So these zones right here would be the mid-oceanic ridges, and as they pull apart, they fracture the lands and create what are called transform faults. And so we get a bunch of almost like stitches at the bottom of the ocean basin where constantly it's being pulled apart by a divergent plate boundary. Because of the dynamics of the ocean floor, the passive and active boundaries, mid-oceanic ridges, deep sea trenches, we have specific types of sediments that are found in certain locations of the ocean. The thickness, of course, is going to vary. Let me be blunt. The thicknesses is going to be thicker where you have less active margins. So I need you to think about what I just said. You'll have thicker accumulations of sedimentary sediments in oceans that are more passive, meaning they don't have as many subduction zones. So the Atlantic Ocean basin has substantially thicker sediments than we do in the Pacific. And the reason is the Pacific is just full of active subduction zones. So in the Pacific Ocean, most of the thickness gets up to anywhere from 1,000 to 1,800 feet thick. That's not very thick. That means the accumulation is pretty slow to have that amount, because we know that the oldest ocean floor sediments date back to 180 million years at oldest best capacity. How do we know that? We poked holes in the ocean floor through the deep sea drilling program, age dated the rock material, and have discovered the ocean floor is exceptionally young. You learned that in plate tectonics. So if the Atlantic Ocean has materials that are up to 3,000 feet thick, that means it's had more time to accumulate. So interestingly enough, the oldest rocks we have on the ocean floor are actually found in the Atlantic Ocean basin. And so when you're looking at that, that's going to be right along the margins of the continent that haven't subducted yet. And so they've had lots of time to accumulate. The most common rocks you're going to find on the seafloor are going to be shales, which are the deep water shales, and then limestone. So the distribution of marine sediments, this kind of shows you along the white edges here, that's going to be your terrigenous materials that have washed off of continents where erosion has occurred. The siliceous oozes we'll get to in a minute and talk about them. They're very distinctive where they live. The biogenous, that is a type of biogenous, but the calcareous ooze makes up everywhere else. So why is that so widespread, that light purple? And then the fine abyssal clay is the pinky stuff all over the place. This is going to be the stuff that's literally the bottom of the ocean mud. So let's take a look at each one of those and talk about how they're made. Terrigenous means derived from land. So it's stuff that's washing off of a continent, an island, and so forth. Biogenous means it's remains of a once living organism that created the sediment. Hydrogenous refers to water-derived sediments. And then cosmogenous, very rare type, but does exist, is derived from outer space. So things like cosmic dust and meteorites material. Obviously, it's going to be a very minute concentration of our sediments. So most of your stuff is going to be in these top two categories right here, terrigenous and biogenous. So what is terrigenous sediment? This shows a pretty good look at that. Let's look at this picture and see this water body is draining into the ocean. And can you see all of this stuff right here? That is terrigenous sediment. When you look at that terrigenous sediment, that's the stuff that's being washed off of the continent and is feeding into the ocean. So this is influencing what type of material would be making up the rocks as those sediments settle out. Fine particles remain suspended for a longer period of time, so if you're clay-sized material, you can go further out into the sea beyond this picture and ultimately end up being part of those pinky areas right back in here. So that can actually happen. Biogenous sediments have three different sources. These are all going to be from shells and skeletons of marine animals and plants that exist in the ocean. Calcareous oozes are macroscopic organisms that live in warm water, especially at the surface. They rely on photosynthesis to live. Siliceous oozes are skeletons of diatoms and radiolarians. They're another type of microscopic organisms. And phosphate-rich materials actually come from the bones, the teeth, and the scales of living animals like fish and other marine organisms that have phosphate-based systems. So calcareous stuff is some of the most common stuff that we have at the bottom of the ocean floor. So let's take a look at another type of sediment. Hydrogenous sediment is minerals that crystallize directly from seawater, things like calcium carbonates, things like manganese nodules, and things like metal sulfides, and even evaporites as sea level rises and falls. And you're seeing some of those right in this area, right in here. What is an iron manganese nodule, since we were looking at hydrogenous topics here? These are lumps of manganese, iron, and other metals that accumulate at the bottom of the ocean floor at very slow rates. They even have growth rings like a tree. You might go, who cares? These are worth a lot of money. Manganese is used in the production of lots of electronics, and so we need it for manufacturing. It's hard to come by. So this is an example of an intrinsic value of the ocean floor. Cosmogenous marine sediments are those that come from outer space, and some of them are macroscopic, some are microscopic, but most are macroscopic. Macroscopic would mean big enough to see, like this right here. This is Tectite Glass right there. Where you find this would be very spotty at best, where we get a meteorite that actually hits the ocean and maybe it shatters, or you get some kind of it washed off of land into the ocean. It's going to be a minuscule amount. So understand that it's out there, but it's not a percentage that you can write home about and say, hey, the ocean's made up of lots of outer space stuff. It's really generated primarily from the remains of dead animals. So when you think about seafloor sediments, I want you to think about coarse-grained terrigenous sediments being close to the shorelines, the continental margin, and the finer grained stuff being further away from that coastline, because the energy of the water can only keep the fine-grained stuff suspended for a long period of time. There are few places in the world that accumulate hardly any seafloor sediments, and the number one place I can tell you you'll see that would be Midoceanic ridges. Instead, the rock you would get there would be lava. The resources for the ocean floor are very important because they produce oil and gas, and even gas hydrates, which are sometimes ice pockets full of methane gas at the bottom of the ocean floor, especially in the continental shelf area for oil and gas in particular. Then you will have things like sands and gravels that have washed off from turbidity currents, making those alluvial fans that we saw at the bottom of the submarine canyons. You'll get things like the manganese nodules we looked at that become a metal resource. Some of these deposits are called placer deposits. They're very important to us for economic gain. Even places that have energy resources can produce, like a hotspot, can produce geothermal energy. So the seafloor provides us lots of great stuff that we use for money. We're going to take a break now, and I'm going to conclude with a sneak peek from one of our next sections and let you think about how these things are formed. And I'll see you back after you've taken a break. Bye.